Good morning, everyone. I'm Tao. I'm a PhD student, work with Dr. Adam Holt and Dr. Sam Goldberg at MGS department. Today, I'm going to share some interesting results from our work on subduction zones. So first, what is subduction zone? It is a place where one tectonic plate sinks beneath another into Earth, and as it happens, it generates earthquake, volcanoes, mountain buildings, and all of this are tied to the interactions between the sinking plate and the mantle below, as shown here by these arrows. And now let's look at where the subduction zones are around the world. We can see that one of the most active regions is at the Western Pacific, which is around the Philippine Sea Plate. And if we zoom in, we use these red and blue arrows to show where is the subduction zone and how its relative motions. We can see this Philippine Sea Plate is surrounded by many subduction zones, and even itself is subducting as well. So it causes a shrinking surface here, and this is also why there has so many earthquakes and volcanoes. And remember, all these geohazards are related to these slab-mantle interactions around the subduction zone. And to constrain these interactions is quite difficult, especially in this tectonic complex region. And here has some geochemical studies says the mantle here is being squeezed out of this region caused by this shrinking surface. But at the same time, there are some geophysical studies say the mantle here may instead flow into these regions. And this mantle flow pathway matters because it will shape the slab-mantle interactions and would also influence where the earthquakes and volcanoes may occur. So here, our goal is to understand how the mantle flow is organized beneath this shrinking Philippine Sea Plate surface, and not only this, but also try to understand the mechanism that drive the mantle flow pathway. So here, we build up our 3D global geodynamic models, embed with realistic slab geometry, lithosphere, and mantle structures, aiming to represent the Earth as closely as we can. And as we get these models, the first thing is to test our models against the observations. So the first one is the plane motions. Here the color looks not good. Here we compare our model and observe the plane motions using this gray and black arrows. We can see on the left side, we see a good global match, and in our focus region, Western Pacific, showing this right side figure, both the direction and the magnitude of the plane motions are well reproduced. And another very important but difficult constraint is the trench motion, which is relative motion at the subduction zones. Here we show our model trench motion in colors and the observations in black. We can see on the left figure, our models will capture the direction of the trench motions. And on the right, you can see our model can also well capture the magnitude of the trench motions. And after we validate our model behavior at the surface, and now we look into the deep mantle. And here we show that mantle floor patterns use these black arrows, and this color map is showing the relative mantle pressures. And when we compare our model result with the geophysical observations shown here at these right sticks, we can see their overall patterns are consistent. They are stressing that the mantle flow here is being flowing into these Philippine Sea Plate regions. And this is because when the Pacific Plate is moving westward here, and it's drag the mantle move with it. But then the flow is stopped by these subducting slab barriers, and then it causes the build up the mantle pressure, and the resulting mantle pressure difference will reorient the flow into the relative low pressure area here, which is the Philippine Sea Plate region. And if we look at this mantle flow pattern into different depths, we can see this pattern are consistent. And here we can see, here we not only observe the outflow squeezed by the surface, but also the inflow. So this raises an interesting question here is the surface is shrinking, and we do not only observe the squeezed outflow, but also there is a strong inflow. So is the mantle beneath the surface is shrinking as well? To answer these questions, we try to quantify the mantle flow in the upper mantle. The first thing is the lateral flow. Here on the left side, we show the different type of lateral flow directions by these arrows, and the numbers show the magnitude. On the left side, on the right side, we combine them together, we get the net lateral inflow here. And at the base of this region, we also quantify the vertical flow through this base. We eventually get the vertical outflow. If we combine these two components together, eventually we get the 3D inflows here. In other words, in this region, there's a gain of material here. So it's telling us the mantle beneath the surface expanding instead of shrinking. So to answer this, we do not only rely on one single models. Instead, we run a range of test models, try to account for the uncertainty of the real Earth condition. So here we list all our test models grouped by different parameter types, and we color them differently, and we validate each models as the same way we did for our reference model. And in the following discussions, we will remove the high misfit cases as low confidence models. So here is the rest of the test models. We can see they all share the similar lateral flow patterns. These bars show the different lateral flow type and their amount. We can see the lateral flow pattern is dominant by this strong inflow through the southeast slab gap. And they all showing us the net lateral inflow with no exceptions. And if we consider the vertical flow, we can see we mainly observe the outflow here. And if we combine them together, the models are telling us the mantle beneath the shrinking surface is expanding. And this raises another interesting question is, if the surface is shrinking, how does the mantle beneath is expanding? So if here we look into the slab motion in the deep mantle, shown here by these black arrows, we can see at the shallow depths, as the figure shown on the left side, on the right side of this region, the slab is advancing. But at the same time, at the left side of this region, the slab is retreating, but more slowly. But if we go deeper into the mantle, we can see this advancing slab turns to be more stable, but at the same time, the left side of the slab starts to retreat rapidly. So if we take a profile here, we can see it will look like this. So this slab converging at the shallow depths will kind of squeeze the mantle, but if we go deeper, the deep slab diverge to enable the submantle is still expanding. So here our take-home message is we observe beneath the shrinking Philippine Sea Plate surface, there is not only the squeeze outflow, but also there's a strong inflow. And this strong inflow forces the submantle to expand and promoting the slab divergence. And this strong inflow also coupled the slab-mantle interactions across different subduction systems. So here will be all my slides, and thank you all for the attention.